Hello everyone. In this short video lecture, we are going to have an example of drawing a Nyquist plot for a system and then determining the stability of the closed loop system using the Nyquist diagram. Here we have the controller in the form of a proportional controller, and GP of S, the plant transfer function, is given as 1 over S plus 1 squared. So basically for L of S, we have K over S plus 1 squared. We want to draw the Nyquist plot and then determine for which values of K the closed loop system is bistable. Before moving to the Nyquist diagram drawing, we can have a quick look at the root locus of the system. For K bigger than 0 values, we here have the root locus plot drawn already. You can see that we have two branches. One is moving towards infinity using one asymptote, and the other one goes towards infinity using the other asymptote. So for K bigger than or equal to 0, the closed loop system will be stable. We can also have a look at the negative locus. If we draw the negative locus, here is minus 1. The point both branches will be on the real axis. One will go towards plus infinity, the other one will go towards minus infinity. And we know that the system will be stable for a given range of K. This point will be the point in which we have the marginal stability. We can determine the value of K over here. You know how to do it by applying the amplitude criterion for the root locus for the system that we have. We have L equal to K over S plus 1 squared. The amplitude plot will tell us, the amplitude condition will tell us amplitude of N over D will be equal to the amplitude of minus 1 over rho. So we will have it in the form of rho 1 over S plus 1 squared, where rho is equal to K. And we evaluate it at S equal to 0 at this point. So if we do so, we will get for amplitude of N over D, we will have 1 over 0 plus 1, which is 1 squared, is equal to amplitude of minus 1 over rho. And we can say that rho will be equal to amplitude of rho will be equal to 1. And since we are on the negative locus, rho will be equal to minus 1, which is equal to K. So we can say that for K bigger than minus 1 and smaller than 0, we have the system stable. But for K is smaller than minus 1, our system will become unstable. And now we can combine the positive locus and negative locus with each other and say that for K bigger than minus 1 and smaller than plus infinity, the system will be stable. For K smaller than minus 1, we will have unstable system with one unstable pole. For the closed loop system, okay, this is what we have for the closed loop system. But now we want to see how we can do this using the Nyquist criterion. So for L of S, we have K over S plus 1 squared. To start, we will set K to 1. Therefore, we will draw the Nyquist plot for L equal to 1 over S plus 1 squared. And then later we will see how we can include the effect of introducing K into our loop transfer function. We can have a look at the body plot for the L of S in terms of 1 plus S plus 1 squared. Here you can see the body plot. For the low frequency, we have 0 dB or 1. Then we have a corner frequency at omega equal to 1 and then the slope that we have here will be equal to minus 40 decibel per decade. In terms of the phase, we start with the phase angle of 0. At omega equal to 1, we'll have minus 90 degrees. And at big values of omega, we will have minus 180 degrees. We want to evaluate L over a contour C1, which includes the whole right half plane. So here we have our contour. Let me wait for, okay, so we have our contour in the clockwise form. As you see here, we have the two poles of L at the point -1. So we can see that there are no open loop poles inside the contour C1. And as a result, P for our Nyquist criterion will be equal to 0. We'll keep that in mind. Now, in order to evaluate or in order to plot the Nyquist mapping for L of S using the contour, we can divide the contour into different segments. The first segment will be here. For that segment, we have S equal to j omega, where omega starts from 0 and it goes towards plus infinity. L of S will be indeed equal to L of j omega, which is 1 over j omega plus 1 squared. And for this segment, we can directly refer to the body plot of the system and find different points like A, B, C, and D, where we have the amplitude and the phase in the new S-plane for the Nyquist plot. So if we start by the point A, we have the amplitude equal to 1 and the phase is equal to 0. So that will be this point. Okay, we have the point A. Amplitude is 1, phase is equal to 0. If we look at the point B, we see that the amplitude is getting a little bit smaller, let's say 0.95 as a rough estimate, and the phase is getting negative. So instead of 0 degrees now, let's say we have minus 20. So if I draw this line here, we have minus 20 degrees, let's say, and the amplitude is a little bit smaller than 1. Then if you consider the point C, the amplitude is getting smaller and the phase now is equal to minus 90, which is this point, minus 90 with an amplitude which is equal to 0.5 indeed. And if we continue, we will get with the point D, where we have the amplitude equal to 0.01 and the phase is close to minus 180, it's minus 160, let's say. Yeah? So here we have minus 160 almost, or maybe minus 150, but the amplitude has become smaller. And if you continue like that, as we move towards the bigger values of omega, as omega approaches infinity, the amplitude gets smaller and smaller, and the phase goes closer to the minus 180, and then we will end up at the origin, okay, where we have the angle equal to minus 180 and the amplitude equal to 0. So basically, this will be the part of the Nyquist plot where we referred to the body plot of the system for the first segment that we had here. For omega starting from 0, going towards infinity. For the next segment, which could be this one, again we have S equal to j omega, but this time omega will start from minus infinity at this point and it will go towards 0. So S will be equal to j omega again, and if we compare it with the first segment that we had over here, what we will get here will be the mirror of the plot for the first segment with respect to the real axis, because only the value of the omega will be multiplied by a negative sign. And therefore, we will have the, let me maybe use another color. We will have the segment number 2 mapped into what you see here. This will give us the direction. Keep in mind that having the direction is quite important, yeah, for the Nyquist plot. So we started at the origin, where we have omega equal to infinity, plus minus infinity indeed. And then as we moved on the imaginary axis towards the origin, we have traveled over this part of the graph, and we ended up at the point A, where we have it over here. You can also see that we have the continuous contour from minus infinity to plus infinity, and over here we also have the continuous, let's say, map, yeah, from omega equal to minus infinity, then we arrived at omega equal to 0, then we continue to arrive at omega equal to plus infinity. Now the last segment that we need to consider is this part. So for that segment, we can say that we have S equal to R e to the power of j theta, where R goes towards infinity, because we want to include the whole right half plane, and theta goes from pi over 2 to minus pi over 2 in a clockwise way. So at this point we have theta equal to plus pi over 2. At some point we reach theta equal to 0, and then at the end we reach the angle of minus pi over 2. So these are what we have. In order to find out the mapping, we need to replace S with R e to j theta. And then we will have L of S equal to 1 over, we have S plus 1 squared, so we'll have R e to j theta plus 1 squared as R goes towards plus infinity. And as R goes towards plus infinity, we can neglect this 1 over here. We will have 1 over R squared e to j to theta as R goes towards infinity, and then we will have 1 over R squared e to minus j to theta, and since R goes towards plus infinity, 1 over R squared will go towards 0. And we will map the whole segment number 3, I can call it. We will map it into the point at the origin. So this will be where we will have the mapping of that segment. And as a result, we will have this Nyquist plot for k equal to 1. So we have now our Nyquist plot for this kind of simple system. We can try to see whether our system is, the closed loop system is stable or not. We already know that P is equal to 0. Now, if we consider the Nyquist plot that we have obtained, and we check the encirclement around the point minus 1, we can say that n is equal to 0 as well, because there are no encirclements of the point minus 1. And then we can determine the z. Z will be equal to p plus n, which is 0 plus 0, and it's equal to 0. So z equal to 0 means that there are no unstable closed loop poles. There are no unstable closed loop poles. As a result, the closed loop system is bistable for k equal to 1. Now, if you want to consider the effect of k, for the positive values of k, if we consider any value bigger than 1, we will have the Nyquist plot over here being inflated. It will be inflated, but you can see that as it becomes, let's say, bigger and bigger, it will never go around the point minus 1. So for any value of k bigger than 1, the Nyquist diagram will not encircle the point minus 1, and as a result, the system will remain stable. For values of k between 0 and 1, the Nyquist plot that we have here will be shrinked, but again, you can see that as it shrinks, it will not encircle the point minus 1, and as a result, we can say that for k bigger than 0, this will be the case. N will remain as 0, and the closed loop system will remain stable. For the negative values of k, the Nyquist plot will be inflated, or it will become shrinked, but it will be also we would need indeed to take into account the effect of the minus sign that we introduce. Yeah. As an alternative way of considering the inflation or the shrinking of the Nyquist plot, we can think of it in the way that I'm going to explain it. Yeah. So we are done with this. So instead of inflating the diagram by the Nyquist diagram by the factor k, or shrinking it by the same factor, we can keep the Nyquist plot as it is, but then scale the x-axis. We can scale the axis by a factor of 1 over k of s, and then we can determine the let's say the number of the encirclements. Instead of the around point minus 1, we consider the number of the encirclement around the point minus 1 over k, and then determine the n, and as a result we can determine the stability of the closed loop system. Let's try it for the system that we have obtained. Yeah? Let me draw it again here. We have our approximate Nyquist plot here. This is the point minus 1. Here we are at the origin. Now, in order to discuss the stability of the system, I will take a point as minus 1 over k, and we now move the point minus 1 over k all along the real axis. If the point minus 1 over k is between minus infinity and the origin, then n will be equal to 0, because the Nyquist plot doesn't encircle the point minus 1 over k. And since p is equal to 0, z will be equal to 0, and our closed loop system will become stable. This is what we have for the positive values of k. If you translate this minus 1 over k between minus infinity and 0, you will get k between 0 and plus infinity. Now, if I move the point minus 1 over k between 0 and 1, we will have one clockwise encirclement. Yes? If the point is here, or here, or here, we will have n equal to 1, and since p is equal to 0, z, which is equal to n plus p, will be equal to 1. And since z is equal to 1, it means that we will have one unstable closed loop pole. The closed loop system will become unstable with one unstable pole. And if you translate this minus 1 over k between 0 and 1, you will get k between minus infinity and minus 1. Now, if I continue to move the point minus 1 over k, if I move it further, so if it's in the area between 1 and plus infinity, let's say somewhere around here or here or here, we see that n will be equal to 0. Since p is equal to 0, z will become equal to 0, and the system will become stable. And you can again translate this minus 1 over k between 1 and plus infinity. It will be translated into k between 0 and minus 1. And now we can put all these together and summarize that for k bigger than minus 1 and smaller than infinity, the closed-loop system will be stable. For k smaller than minus 1, we will have unstable system with one unstable pole. And we can say that we are done with in terms of analyzing the stability of this system using the Nyquist plot. Alright, so that's all for this video. In the next video, we'll go through another example and I will show you how to draw the Nyquist plot for a different system and how to analyze the stability of the closed system using the Nyquist plot. Thank you for watching and see you in the next video.